A world where the sun never moves. What would it actually feel like to stand on a planet where the star never moves? To look up at the sky and see a dim, reddish sun frozen in place, forever hanging over the same horizon. One side of the world locked in eternal daylight, the other plunged into endless night, and in between, a narrow band of permanent sunrise. We are used to thinking that a day means motion. The sun rises, crosses the sky, and sets. Time itself feels tied to that rhythm. But while that cycle defines life here, it's a lot harder to imagine what morning or evening would mean on a tidally locked planet where the same face always points toward its star. Would there be climates at all, or just a scorched dayside and a frozen wasteland in darkness? Could such a place ever be truly habitable? This leads to a deeper question about our place in the universe. Are we living on the only kind of world that can host complex life, with a spinning globe and a moving sun? Or is Earth just one version among many, one example in a vast catalog of strange but still livable planets? In the hunt for alien life, this is not just philosophy. This is a testable question. And right now, one of the best laboratories for that test is a small, faint red dwarf star about 40 light-years away, TRAPPIST-1, a system of 7 rocky, Earth-sized planets, all packed in close, all almost certainly tidally locked. Among them, one world stands out as our prime suspect for an alien Earth under very different rules, TRAPPIST-1e. TRAPPIST-1e is almost the same size as Earth, with a similar density, orbiting in the middle of the star's Goldilocks zone. But it races around its star in just over 6 days, so close that tidal forces have frozen its rotation. This means one hemisphere faces the star forever, while the other never sees it at all. If there is an atmosphere, and maybe an ocean, they would have to redistribute heat between day and night, smoothing out extremes, and deciding whether the planet is a scorched desert, an icy shell, or something far more interesting. Until recently, this was mostly theory. We had models, simulations, and educated guesses. But it should be noted that the James Webb Space Telescope has now given us our sharpest look yet at TRAPPIST-1e. For the first time, we have real data on its temperature and the kinds of atmospheres it probably does not have. So it's time to find out the truth about what kind of world we are actually dealing with. By the end of this video, we will go far beyond abstract numbers. We will build a vivid picture of a day in the life on TRAPPIST-1e. From the unmoving star in the sky, to the permanent twilight ring around the planet, to the cities, ecosystems, and even civilizations that might adapt to such a frozen dance of light and darkness. So let's begin. Why this one planet could rewrite our place in the cosmos. But why does this one distant world matter so much to us? If we are going to imagine a day in the life on TRAPPIST-1e, we first have to understand why this small planet could completely reshape how we see our place in the universe. In the hunt for alien life, there has been one driving question for decades. Is life a freak accident of Earth, or a common outcome whenever conditions are right? We only have one confirmed example, our own planet, which is scientifically frustrating. So if we want to know whether life is rare or routine, we need other Earth-like laboratories. Worlds that are close enough to our own to make a fair comparison, but different enough to test the rules. TRAPPIST-1e is one of the best of these tests. It sits in the middle of its star's Goldilocks zone, receiving about 2/3 of the energy Earth gets from the sun. It is almost the same size and density as Earth, with a rocky composition and likely an iron core. This means we are not dealing with a gas giant, a mini Neptune, or a frozen dwarf. We are looking at a solid, temperate planet where liquid water could exist, at least in principle. But while Earth orbits a bright, short-lived yellow star, TRAPPIST-1e circles an ultra-cool red dwarf. It should be noted that this type of star burns fuel incredibly slowly. Our sun will last about 10 billion years in total. TRAPPIST-1 could shine for trillions. If a stable, habitable atmosphere can survive around such a star, then the galaxy might be filled with long-lived homes for life that outlast Earth by a factor of 1,000. Optimistically speaking, that is an almost unimaginable expansion of the possible timelines for biology and even civilization. The difficulty is that we cannot go there. We cannot scoop up soil, sail its oceans, or fly through its atmosphere. All we have are tiny dips in starlight as the planet passes in front of its star, and faint heat signatures as it moves through its orbit. This means every photon of data from TRAPPIST-1e is precious, and also ambiguous. Is a missing signal proof that there is no atmosphere, or that the atmosphere is just different from what we expected? So it's time to find out the truth about what is really at stake. If TRAPPIST-1e turns out to be habitable, with a stable atmosphere and surface temperatures that allow liquid water, then life may not be a cosmic fluke at all. It would suggest that Earth-like planets around calm red dwarfs are natural, even frequent outcomes of planet formation. But if TRAPPIST-1e is airless, stripped by its star's early radiation, or locked into a deep freeze, then it becomes a warning. A sign that atmospheres are fragile, that even perfect-looking orbits can hide dead worlds. So out of thousands of exoplanets, why has this one dim red dwarf with its 7 tightly packed worlds become the poster child for alien Earths? And what, exactly, makes TRAPPIST-1e stand out from its siblings? Meet TRAPPIST-1, the tiny star with 7 Earths. To answer that, we have to meet the star at the center of all this drama. TRAPPIST-1 is not a blazing sun like ours. It is an ultra-cool red dwarf, barely bigger than Jupiter in size, but far more massive, quietly glowing about 40 light-years away in the constellation Aquarius. In the hunt for alien life, that distance is practically next door on galactic scales. Yet what really makes this star special is not the star itself, but what is packed tightly around it. Instead of a few widely spaced worlds, TRAPPIST-1 hosts 7 planets, all roughly Earth-sized, all huddled closer to their star than Mercury is to the Sun. Imagine compressing an entire planetary system into a space smaller than the orbit of our innermost planet. If TRAPPIST-1 were placed at the center of our solar system, every one of its worlds would comfortably fit well inside Mercury's path, forming a compact, clockwork chain of orbits. Does that sound crowded? It is, in the best possible way. The planets are named TRAPPIST-1b through TRAPPIST-1h, in order of their distance from the star. So let's begin with their layout. The inner worlds, B and C, are baked by intense radiation. Further out, D, E, and F sit in what astronomers call the classical habitable, or Goldilocks zone, where temperatures could allow liquid water on a planetary surface. Beyond them, G and H drift in the cooler outskirts. This means 3 of these 7 planets, at least on paper, could be potentially habitable. But while D, E, and F all pass the basic distance test, one of them stands out. TRAPPIST-1e sits right in the middle of the Goldilocks zone and hits a remarkable sweet spot of size, density, and stellar energy. It receives about 2/3 of the light that Earth gets from the Sun, similar to a cool, temperate region on our own planet. It should be noted that this balance is rare among known exoplanets, especially around such a small, dim star. The numbers make it even more intriguing. TRAPPIST-1e has a radius about 0.92 times that of Earth and a mass around 0.77 Earth masses. In other words, it is slightly smaller and lighter than our world, but not by much. Its density points strongly to a rocky composition with a substantial iron core. Optimistically speaking, this is not a puffy mini Neptune wrapped in thick hydrogen and helium. This is a solid, Earth-like planet. So it's time to find out the truth about this system. On paper, TRAPPIST-1 looks like a paradise of 7 potentially habitable worlds, tightly choreographed around a gentle red dwarf. But the type of star at its center usually spells trouble for atmospheres and life. What happens when fragile, Earth-sized planets live this close to a restless red dwarf? JWST enters the scene, turning a pixel into a world. What if we could actually watch those fragile planets struggle against their restless star? Until very recently, TRAPPIST-1e was almost nothing more than a line in a spreadsheet. Mass, radius, orbit, and a big blinking question mark where words like ocean, clouds, or atmosphere should be. We knew it was roughly Earth-sized. We knew it sat near the middle of the Goldilocks zone where liquid water could exist. But while theory can sketch a planet, it cannot tell us what it feels like. Is TRAPPIST-1e a steaming greenhouse, a frozen snowball, or a truly habitable, Earth-like world? On paper, all three were possible. In the hunt for alien life, that kind of uncertainty is both exciting and deeply frustrating. So what changed? A 6.5 meter eye in space, chilled almost to absolute zero, unfolded its golden mirrors and turned toward this tiny red dwarf system. The James Webb Space Telescope is not just another observatory. It should be noted that it was designed from the ground up to read the faint fingerprints of molecules, especially in the infrared, where cool stars and temperate planets quietly shine. Webb sits at the Sun-Earth L2 point, a gravitational parking spot about 1.5 million kilometers from us. From there, it can stare at TRAPPIST-1 for hours, watching each planet orbit across the face of the star. How does that help? When TRAPPIST-1e passes in front of its star, a bit of starlight filters through any atmosphere it has. Different gases absorb different colors, leaving tiny dips in the spectrum. This means, in principle, we can tell whether there is CO2, water vapor, methane, or almost nothing at all. Then there is the flip side of the orbit. When the planet slips behind the star, Webb briefly sees the system without the planet's own glow. Subtract the before and after, and you get a direct measure of the planet's thermal emission. Is the day side blazing or merely warm? Does heat spread to the night side, hinting at thick air or oceans? Or does it radiate straight back into space, like bare rock? Here is where the story turns into a kind of cosmic courtroom drama. So let's begin with the inner worlds, because that is exactly what JWST did. First on the stand, TRAPPIST-1b and TRAPPIST-1c. Were these close-in planets wrapped in puffy hydrogen atmospheres, or swaddled in dense CO2 like a miniature Venus? Or were they almost airless, their surfaces exposed directly to the star? The early verdict was surprisingly harsh. Webb's data showed these planets are cooler than a thick atmosphere would allow, and their spectra lack the broad signatures of hydrogen envelopes. Optimistically speaking, that is bad news for B and C as homes for life, but very good news for us as detectives. It proves JWST can dissect these tiny worlds. So it's time to find out the truth for TRAPPIST-1e. In the rest of this video, we will follow Webb's evolving verdict as it moves outward through the system and then zoom in on what the measurements imply for climate, oceans, and daily experience on this one special planet. Habitable or hostile? The TRAPPIST-1e coin flip. So what is TRAPPIST-1e really? A gentle blue world with clouds, oceans, and a breathable sky? Or a bare, lightless rock, its surface sterilized by its tiny red dwarf star? In the hunt for alien life, this is where the story sharpens into a coin flip. On one side, we have the hopeful tale. TRAPPIST-1e is almost perfectly Earth-like in size and density, with a rocky composition and a likely iron core. It sits right in the middle of the Goldilocks zone, receiving about 2/3 of the energy Earth gets from the sun. This means, with the right atmosphere, its surface temperature could easily allow liquid water. But while those numbers sound comforting, the other side of the coin is far less friendly. To get that just right energy from such a cool red dwarf, the planet has to orbit incredibly close in, whipping around its star in just over 6 days. It should be noted that at that distance, TRAPPIST-1e is almost certainly tidally locked. One hemisphere faces eternal day, The other, endless night. Without a thick, active atmosphere and maybe oceans to move heat around, one side could freeze solid while the other bakes. And then there is the star itself. TRAPPIST-1 is quiet for a red dwarf, flaring about 30 times less than its cousins, but it is still a red dwarf. That means intense ultraviolet and X-ray radiation early in the system's history, the kind of stellar tantrums that can strip atmospheres away, molecule by molecule. So, let's begin to see why this is such a dramatic question. Does TRAPPIST-1e still have air at all? JWST's first verdict on the inner planets gives us a mixed message. For TRAPPIST-1b and 1c, Webb sees no evidence of thick, hydrogen-dominated envelopes. No mini-Neptunes here, which is good news if we want solid, potentially habitable surfaces. But those same observations also suggest these worlds are effectively airless, or left with only the thinnest skins of gas. Optimistically speaking, this clears away one bad option, while raising a more existential worry. If close-in planets lose even modest atmospheres, where does that leave 1e? This means TRAPPIST-1e becomes a test case for the entire galaxy. If it can hold on to a stable atmosphere in this harsh radiation environment, then many other red dwarf planets might be habitable too. If it cannot, vast swaths of the universe's most common planetary systems suddenly look far less promising. So it's time to find out the truth. When we eventually simulate standing on TRAPPIST-1e, are we breathing, swimming, and building under a dim red sun, or crunching across frozen, airless rock beneath a nearly black sky? In the next part, we will push JWST's data to its limits and try to feel what that alien day or endless night would actually be like. Here's how we're going to explore this alien Earth. So, let's begin our actual journey to this alien Earth. If you are new here, we explore real exoplanet science and then push it one step further, asking what it would actually feel like to stand there, breathe there, and maybe even build a civilization there. I'm your guide through this, but the real star of the channel is the data itself. In the hunt for alien life, we let telescopes like JWST lead, and our imagination follows. To make sense of TRAPPIST-1e, we need a clear roadmap. Otherwise, 7 planets, 1 red dwarf, and a mountain of observations just blur together. So what are we going to do step by step, and how will we know if this world is really habitable or secretly hostile? First, we will go big. We start with the star. TRAPPIST-1 is an ultra-cool red dwarf, and everything about its planets flows from that. How much radiation does it produce? How often does it flare? Does it strip atmospheres or gently warm them? It should be noted that if the star is too violent, even the most Earth-like orbit in the Goldilocks zone may not save a planet. Then we zoom out to the entire TRAPPIST-1 system. 7 Earth-sized planets, all packed closer than Mercury is to our Sun. Which ones are scorched? Which are icy? Why does 1e stand out from its siblings as the most promising Earth-like candidate? By comparing them, we will see what makes a planet cross that thin line between living and dead. Next comes the physics that will define our view from the ground. Tidal locking and climate. What does a day mean when the star never moves in the sky? Does the world freeze on the night side while the day side boils? Or can a thick atmosphere and oceans smear that heat around into something surprisingly comfortable? This means we will need to talk about eyeball Earths, endless sunsets, and strange wind patterns. Only then do we bring in JWST's verdict. We will dissect what its infrared eyes tell us about TRAPPIST-1e's temperature, atmosphere, and possible clouds. Which types of atmospheres are already ruled out, and which remain on the table? Optimistically speaking, we might be left with a narrow but exciting window where liquid water and life could exist. Finally, we dive all the way down to the surface. Weather, skies, oceans and ice, forests or barren rock. If intelligent life arose here, how would cities look under a dim red sun that never sets? How would culture evolve without seasons or moving constellations? As we go, keep score in your head. Each new fact will nudge TRAPPIST 1E one step toward habitable or hostile. By the end, you should be able to close your eyes and visit this world, a scientifically grounded trip to an alien Earth. So it's time to find out the truth, starting with the star that controls everything. First principles. What makes any planet livable? If we want to know whether TRAPPIST 1E could truly host life, we have to ask a deeper question first. What does it even mean for a planet to be habitable? Habitability is not a single on-off switch. It is a balancing act between energy from the star, the size and composition of the planet, its atmosphere, its magnetic field, and even how geologically restless it is beneath the surface. In the hunt for alien life, we often start with the star. How bright is it? What color or spectrum does it shine with? Does it live for billions of years or burn out quickly? And crucially, for a red dwarf like TRAPPIST-1, how often does it unleash violent flares that can strip away a planet's atmosphere? A calm, long-lived star with steady output is like a reliable power supply for any potential biosphere. But while the star sets the stage, the planets decide how the story plays out. Mass and radius tell us gravity. Gravity shapes whether a world can hold on to an atmosphere. Rotation and orbit control the length of day and the pattern of seasons. Oceans, if they exist, move heat around and stabilize climate. This means two planets in the same system, at the same distance from the same star, can end up as a frozen snowball and a steaming greenhouse. So let's begin with a term you have almost certainly heard, the habitable zone, the famous Goldilocks zone. It is the range of orbits where, in principle, liquid water could exist on a planet's surface. Not too hot, not too cold. TRAPPIST-1E sits right in the middle of this band for its tiny red dwarf star. It should be noted that this sounds like a promise of oceans and beaches. It is not. It is only a rough guideline for incoming energy, not a guarantee of Earth-like conditions. Why? Because everything depends on what the planet does with that energy. A thick CO2 atmosphere can trap heat and turn a Goldilocks world into a Venus-like inferno. No atmosphere at all, and even a perfectly placed planet becomes an airless, frozen rock once the star dips behind local terrain. Optimistically speaking, TRAPPIST-1E scores well on size and density, suggesting a rocky, possibly Earth-like composition. But its true atmosphere and magnetic protection remain uncertain. And here is the abstract difficulty. From 40 light-years away, we mostly see orbits and sizes. We measure how the star's light dips as each planet passes in front. From that sparse data, we have to infer climate, clouds, and surface oceans, using models and a few indirect spectral fingerprints. It is like trying to reconstruct an entire world from a shadow on a screen. So it's time to find out the truth about TRAPPIST-1E's chances. To do that, we cannot start with the planet itself. We have to start with the small, strange star that sets all the rules, and ask whether its quiet glow can really support an alien Earth. The star at the center, TRAPPIST-1's strange personality. So what kind of star are we asking to host an alien Earth? Evaluating a planet's chances for life is impossible without first understanding the furnace at its center. In the hunt for alien life, the star is not just background scenery. It is the main character that sets the script. TRAPPIST-1 is what astronomers call an ultra-cool M-dwarf, the smallest, faintest kind of red dwarf star. It has only about 9% of the Sun's mass, and its diameter is roughly the size of Jupiter's. This means you could almost line it up next to our gas giant and not see much difference in size, even though it is still more than 80 times more massive. It glows a deep red in visible light with less than 1,000th of the Sun's luminosity. It should be noted that this makes TRAPPIST-1 utterly ordinary on a cosmic scale. Red dwarf stars like this are the workhorses of the Milky Way. They make up the majority of stars in our galaxy, and their cool, stingy fusion allows them to burn for trillions of years. That is hundreds or thousands of times longer than the Sun's total lifetime. So if you wanted a star that could keep a habitable planet warm for almost the entire age of the universe, a red dwarf is a tempting choice. But while that sounds perfect, there is a catch. Several catches, actually. Because these stars are so dim, their Goldilocks zone is pulled in extremely close. Any planet that wants liquid water has to huddle right next to the star. This means the planet's orbit slows and locks, so one hemisphere permanently faces the star, while the other faces away. Tidal locking turns a normal day-night cycle into a world of eternal noon on one side and endless night on the other. Is that really a place where an atmosphere can survive? On top of that, red dwarfs are often magnetically active. They can unleash powerful stellar flares and bathe nearby planets in high-energy radiation and charged particles. Their early lives are especially violent, with intense outbursts that can last hundreds of millions of years. This means any young Earth-like world in close orbit might have its atmosphere stripped away long before life has a chance. TRAPPIST-1e is deep in this danger zone. It orbits so close that a year lasts only about 6.1 Earth days. The star would loom several times larger in the sky than our sun does from Earth, a swollen crimson disk hanging over the day side, even though it is intrinsically much dimmer. Optimistically speaking, that huge red star could provide a steady, gentle glow, but it could just as easily be a relentless source of radiation. So let's begin to weigh the odds. On paper, this combination of tight orbit, tidal locking, and a flare-prone stellar type should be terrible news for atmospheres. So it's time to find out the truth. Is TRAPPIST-1 the atmospheric executioner we fear? Or is this particular red dwarf hiding an unusually calm personality that might let TRAPPIST-1e stay truly habitable? A surprisingly quiet red dwarf. Hope for atmospheres. To answer that, we have to ask a deceptively simple question. Just how angry is this star, really? For years, the default assumption was brutal. An ultra-cool red dwarf, with planets huddled close in its Goldilocks zone, should be a relentless blowtorch of flares and high-energy radiation. In the hunt for alien life, that kind of environment usually goes straight into the probably hopeless folder. But TRAPPIST-1 has surprised us. When astronomers actually watched it in detail, they found that while it does flare, it is far from the worst offender. Compared to many similar M-dwarfs, TRAPPIST-1 seems almost restrained. It should be noted that earlier models assumed fierce X-ray and ultraviolet bombardment, constant atmospheric stripping, and worlds left airless in a few 100 million years. The new data paint a softer picture. So what does softer mean in numbers? Observations with X-ray telescopes and ultraviolet instruments suggest that TRAPPIST-1's high-energy output is significantly below the nightmare scenarios. Large, powerful flares appear perhaps a few times per year, not dozens per month. Its average X-ray and extreme UV flux at the orbits of planets like TRAPPIST-1e is estimated to be several times Earth's, not hundreds of times. This means the planets are stressed, but not necessarily doomed. To see why that matters, we have to talk about atmospheric erosion. High-energy photons slam into the upper atmosphere, heating it, breaking molecules apart, and giving particles enough speed to escape a planet's gravity. At the same time, a charged particle stream, called the stellar wind, can physically strip gas away. Over billions of years, that combination can peel an atmosphere off completely. But while intense radiation and wind erode, a strong planetary magnetic field can shield, deflect, and buy time. Here is where TRAPPIST-1e becomes especially interesting. It is dense and Earth-like, suggesting a metallic core that could power a magnetic dynamo. If TRAPPIST-1e has even a moderately strong magnetic field, and the star is only a few times harsher than the Sun instead of 100 times, the balance may tip toward atmospheric survival over billions of years. Optimistically speaking, that is a very different story from the one we once told about red dwarf systems. Remember that earlier list of problems? Tidal locking, close orbits, vicious flares? Those are still real challenges. But while many red dwarfs behave like cosmic flamethrowers, TRAPPIST-1 looks more like the calm one in a rough neighborhood. So let's begin to see it not just as a threat, but as an unusually promising laboratory for habitable worlds. This relative calm is exactly why TRAPPIST-1e has become the poster child for potentially habitable red dwarf planets. So it's time to find out the truth of what that might feel like on the surface under a dim red sky that never moves. How we found a family of 7 Earths around a tiny star. But how did we even find this supposedly calm, dim little star hiding a whole family of Earth-sized worlds in the first place? In the hunt for alien life, that story matters because it tells us what our telescopes can really do and what they might be missing. The tale begins not with a giant space observatory, but with a small, very patient telescope on the ground. The TRAPPIST project, that is, the Transiting Planets and Planetesimals Small Telescope, used modest instruments in Chile and Morocco to stare at faint red dwarf stars night after night. The strategy was simple but powerful. Watch for tiny, regular dips in starlight that might betray a planet crossing in front. This is the transit method in action. When a planet moves across the face of its star, it blocks a fraction of the light, like a moth briefly fluttering across a lamp. The star appears to dim by a tiny amount, then brighten again. If that dip repeats with a steady rhythm, we know there's a planet in orbit. The depth of the dip tells us the planet's size. The time between dips reveals its year. It should be noted that this technique is especially effective for small, cool stars because an Earth-sized planet blocks a larger fraction of their light. In 2016, TRAPPIST watched one such star, later named TRAPPIST-1, and saw not one, but a repeating pattern of dips that could only be explained by 3 different planets. 3 Earth-sized worlds, all packed close to a single red dwarf. Already, that was astonishing. But while 3 planets were exciting, the data hinted that the story was incomplete. Some dips overlapped, some timings were off, something else was tugging on these worlds. So larger telescopes joined the effort. The Very Large Telescope in Chile, the Spitzer Space Telescope in orbit, and others locked onto TRAPPIST-1 and collected more precise data. As months of light curves piled up, astronomers realized they were not looking at 3 planets at all. They were seeing 7. 7 Earth-sized planets, all transiting, all in a compact chain of orbits, each one gravitationally nudging the others in a delicate dance. This means we can do more than just count them. The way the planets tug on each other lets us estimate their masses. Combined with their sizes from the transit depths, we get densities. And those densities are crucial. They show that all 7 are roughly Earth-sized and consistent with rocky compositions, not bloated gas giants. Optimistically speaking, this is exactly the kind of system we dream about when we talk about habitable, Earth-like worlds. A rare, tightly packed family of rocky planets, all crossing a small, cool star right in front of our telescopes. TRAPPIST-1 has effectively become a natural laboratory, perfectly set up for JWST to probe their atmospheres and test our ideas about the Goldilocks zone. But what has JWST actually seen when it stares at TRAPPIST-1e's thin red daylight? And what has it ruled out? 7 worlds, 1 question. Which could host life? So if JWST can now peer straight through that thin red daylight on TRAPPIST-1e, what does it tell us about the whole family it lives in? Because this is not just one tempting world in isolation. This is a chain of 7 planets, B through H, all roughly the size of Earth, all packed closer to their tiny red dwarf star than Mercury is to the Sun. In the hunt for alien life, that sounds like hitting the cosmic jackpot, right? On paper, it almost does. 3 of these worlds, D, E, and F, sit in the traditional Goldilocks zone, where a planet could, in principle, keep liquid water on its surface. Not 1, not 2, but 3 just right orbits in a single system. It should be noted that this is exactly the sort of architecture we dreamed of finding when we first started talking about habitable exoplanets. But while the orbits look friendly, the star itself tells a harsher story. TRAPPIST-1 is an ultra-cool red dwarf, and like most of its kind, it spent its youth blasting its planets with high-energy radiation and powerful stellar winds. The planets are so close in that they are almost certainly tidally locked. One face in eternal day, one in endless night. This means any atmosphere has had to survive billions of years of stripping, heating, and constant stress. So let's begin to ask the uncomfortable question. In a system that looks so promising from a distance, does any planet actually cross the line into truly habitable? Or are they all, in different ways, victims of their star's environment? Each world offers a different experiment. TRAPPIST-1b and 1c, huddled closest to the star, are simply too hot. JWST's thermal data show surfaces that radiate like bare rock, with at most a whisper of CO2, effectively airless, scorched, and dry. On the far side, planets G and H are so cold and weakly lit that without a thick insulating shroud of gas, they likely freeze into deep global ice. That leaves the middle ground. Planet D, at the inner edge of the Goldilocks zone, may have lost more water than it kept. Planet F, farther out, may be a high-pressure steam or ice world. Between them sits TRAPPIST-1e, receiving about 2/3 of Earth's light, with an Earth-like density and no bloated hydrogen envelope. Optimistically speaking, it is the best all-around candidate for a truly temperate, rocky, potentially habitable surface. So it's time to find out the truth. If even TRAPPIST-1e, the golden child of the system, the one that checks almost every box, turns out to be barren, what does that say about the odds of life around the most common stars in the universe? And what exactly would we expect to see on a world that passes this brutal test? Reading shadows and heat. How certain are we, really? But before we move in and start sketching oceans, cities, and alien forests, we need to pause. How much do we actually know about TRAPPIST-1e? And how much are we carefully, responsibly imagining? In the hunt for alien life, this is where things get surprisingly fragile. Everything we say about this planet comes from indirect measurements. We do not have a photograph of continents and clouds. We have light curves, tiny dips in starlight as the planet crosses its red dwarf star. We have spectra, the faint fingerprints of different molecules, blurred by distance and noise. And we have models, thousands of them, testing what kind of atmosphere and surface could produce the patterns we see. This means that when we talk about TRAPPIST-1e, we are reading shadows and heat, not rocks and oceans. JWST never sees the planet as a resolved disk. Instead, it watches the system's brightness rise and fall as each world orbits, then extracts a temperature map and possible atmospheric signal from that changing glow. It should be noted that even with a telescope as powerful as JWST, that is an incredibly subtle measurement. So where are we right now? Early JWST campaigns focused on the inner planets, B and C. By measuring their thermal emission, astronomers found that both are cooler than a bare rock facing the star should be, yet show no clear atmospheric absorption. The best explanation is that they are effectively airless, or at most, have vanishingly thin carbon dioxide envelopes. TRAPPIST-1, D, E, and F are now being targeted in a series of deeper observations, building up transit by transit. For 1E, we already have preliminary constraints, but no definitive atmospheric detection yet. Here is the pattern interrupt. When scientists say, no thick hydrogen atmosphere, or consistent with a bare rock, they are not declaring with absolute certainty what is there. They are ruling out what is not. A Jupiter-like hydrogen blanket? Gone. A Venus-style crushing carbon dioxide shroud? Also very unlikely. Even a Mars-like thin CO2 atmosphere as the dominant component seems disfavored by the current data. But a mixed nitrogen CO2 atmosphere, or one rich in water vapor, or patchy clouds over an ocean world, those are still very much on the table. And all of this is a snapshot in time. JWST will keep watching this system for years. As more orbits stack up and analysis techniques improve, our picture of this supposedly Earth-like world may sharpen or change completely. Optimistically speaking, we might even see hints of weather or seasonal variations or unexpected chemistry. So let's begin the speculative part with clear boundaries. When we talk about daily life on TRAPPIST-1e, about ecosystems, or even civilizations under a fixed, dim, red sun, we will flag that as informed imagination built on the best physics and the best data we have today. The next sections are where we step onto that world and ask, if it is truly habitable, what would it actually feel like to stand there? Zooming out, how habitable is the TRAPPIST-1 system overall? So if we are about to step onto TRAPPIST-1e in our imagination, we should first zoom out. What kind of planetary neighborhood are we actually walking into? In the hunt for alien life, astronomers rarely get a whole family of worlds delivered on a silver platter. Yet that is exactly what TRAPPIST-1 gives us. 7 Earth-sized planets around a single, ultra-cool red dwarf star, all packed into a space smaller than Mercury's orbit. This means we are not judging one lonely world, but an entire compact system where patterns start to emerge. On the basic habitability scorecard, 3 planets stand out. TRAPPIST-1d, 1e, and 1f. They sit in the classical Goldilocks zone, where the energy from the star could in principle allow liquid water on the surface. Planet E is almost perfectly centered in this band, receiving about 2/3 of the light Earth gets, while D bakes slightly closer in, and F chills a little farther out. Already, that gives us 3 separate shots at a temperate, Earth-like environment in one place. But while our own solar system spreads its planets across vast distances, TRAPPIST-1 is incredibly compact. All 7 planets orbit well inside where Mercury circles the Sun. Their years are measured in days, not months. They form a resonant chain, locked into rhythmic orbital relationships so precise that the planets regularly tug on each other, subtly stretching and squeezing their interiors. From the surface of one planet, the others would not be tiny pinpricks of light. They could loom large in the sky, crescents and disks you could point at with the naked eye. Optimistically speaking, this tight configuration is almost perfect for habitability studies. A long-lived red dwarf star, 7 rocky worlds, and 3 in the habitable zone means the universe has had multiple chances to try out life here. It should be noted that this is also perfect for us as observers. The frequent transits and strong gravitational interactions make it easier for telescopes like JWST to measure masses, radii, and even sniff for atmospheres. So it's time to find out the truth about the downside. The same compactness that helps us could be dangerous for the planets. Being so close to the star means they share the same flare environment, the same high-energy radiation, and potentially the same long-term erosion of their atmospheres. If TRAPPIST-1's activity stripped one habitable world bare, it might have done the same to all of them. This system could be a grand success story for life, or a synchronized failure. To untangle that, we cannot stay zoomed out. We need a planet-by-planet tour, using the same questions each time. How much energy do they get? Do they keep an atmosphere? Could liquid water exist? We will start at the inner edge, with TRAPPIST 1D, move outward through E and F, and then finally choose one world as our home base. When we arrive at TRAPPIST 1E, the data becomes strangely compelling, and the picture of daily life under a dim red sun becomes very hard to ignore. Inner fire, TRAPPIST 1B and 1C, the two hot siblings. So let's begin our planet-by-planet tour, not with the hopeful worlds, but with the dangerous ones. If we want to understand what makes TRAPPIST 1E special, we first need to see what happens when a planet strays too close to its star. Meet TRAPPIST 1b, the innermost world of the system. It orbits the red dwarf once every 1.5 Earth days, so a year there is shorter than a weekend here. At that distance, it receives several times more energy than Earth does from the sun. This means its day side is likely scorched to temperatures where rock can soften, and any surface water would be long gone as vapor. In the hunt for alien life, this is not where we would place our first bets. TRAPPIST 1b is roughly Earth-sized, with a similar radius and mass, so its surface gravity would feel surprisingly familiar. For a long time, some scientists wondered whether it might be a mini Neptune, wrapped in a thick blanket of hydrogen and helium, but JWST has now stepped in as judge and jury. Using its infrared vision, it has ruled out a puffy, Neptune-like hydrogen atmosphere. It should be noted that this is a dramatic result. What we are left with is almost certainly a rocky planet, either nearly airless or cloaked in only a thin, probably eroded atmosphere, stripped over billions of years by intense stellar radiation. Just a little farther out lies TRAPPIST 1c. Its orbit is still incredibly tight, only about 2.4 Earth days. From its skies, the red dwarf would loom huge and dimly red, yet still deliver too much energy for conventional surface liquid water. TRAPPIST 1c is cooler than B, but still well inside the inner edge of the classic Goldilocks zone. Optimistically speaking, it is more Earth-like in composition, likely a dense, rocky world with an iron core. Yet JWST data again suggest that if any atmosphere exists, it is thin and probably dominated by heavy molecules like carbon dioxide, not the thick protective envelope that a truly habitable world would need. So what do these inner siblings really teach us? They are cautionary tales. They show us what close-in, irradiated planets around this star look like when the furnace is turned up too high. We see that intense stellar energy and long-term radiation can erode atmospheres, bake surfaces, and push worlds far away from the conditions needed for life as we know it. This means that as we move outward through TRAPPIST 1D and toward TRAPPIST 1E, we must pay close attention to a delicate balance. How much energy can a planet receive and still keep an atmosphere? Where is the tipping point between a bare rock and a temperate, potentially habitable surface? So it's time to find out the truth by stepping just beyond these two hot siblings into the narrow band where survival becomes far more finely tuned and far more interesting. The edge of comfort, TRAPPIST 1D, 1F, 1G, and 1H. So if 1C was already flirting with disaster, what happens when we step just inside the true inner edge of the Goldilocks zone? TRAPPIST 1D is where that question becomes very real. This planet whips around the red dwarf in about 4 Earth days. A year there is shorter than most of our work weeks. It receives more energy from its star than Earth does from the sun, so its day side could be warm, even tropically hot. But while that sounds promising for liquid water, it also pushes 1D right up against the threshold where oceans can start to boil away. In the hunt for alien life, that balance is everything. If TRAPPIST 1D has a dense atmosphere and a deep global ocean, the day side might be wrapped in thick clouds and steam, with heat carried to the night side by powerful winds. If its atmosphere is thinner, the day side could be scorching, while the night side freezes solid. JWST has not clearly detected water vapor, CO2, or methane yet, but it should be noted that a heavy, cloud-rich atmosphere could easily hide from our instruments. Now we slide past 1E and move outward to TRAPPIST-1F, just beyond the middle child of the system. This planet orbits every 9 days and receives less stellar flux than Earth. On paper, that makes it a cooler world, one that might resemble a snowier version of our planet. Ice sheets could creep outward from the night side, and even the day side might be locked in a kind of permanent winter unless a strong greenhouse effect steps in. This means that atmosphere is destiny for 1F. Give it a thick blanket of CO2 or other greenhouse gases, and you could warm the surface enough for pockets of liquid water, perhaps beneath thin ice. Leave it with only a modest atmosphere, and it may become a mostly frozen, glaciated globe. Beautiful, but harsh. Beyond that, we reach TRAPPIST-1G and 1H, the outermost siblings. Their orbital periods stretch longer, their share of the star's light drops dramatically, and their surfaces are likely far colder. Think less Earth-like ocean world, more icy moon of Jupiter or Saturn. Optimistically speaking, internal heating from radioactive elements or tidal flexing could keep subsurface oceans liquid, but without substantial atmospheres, their surfaces would be deeply frozen. So let's begin to see the pattern, from too hot near 1D to too cold at G and especially H. The system forms a clear gradient in energy. And sitting right in the middle of this cosmic thermometer is TRAPPIST-1E, the planet whose incoming energy most closely matches Earth's temperate zones. So it's time to find out the truth. After everything we have seen, what exactly makes 1E stand out as our best shot at an alien Earth? And what is JWST already whispering to us about its hidden atmosphere and climate? What if the next set of data finally tips the scales? TRAPPIST-1E, the most Earth-like world we've found? If we line up all 7 worlds of the TRAPPIST-1 system, one question rises above the rest. Which of these actually feels like a place where we could stand, walk, and maybe one day breathe? In the hunt for alien life, one planet keeps pulling our attention back: TRAPPIST-1E. So let's begin with its path around the star. TRAPPIST-1E completes a full orbit in just about 6.1 Earth days. A year there would pass between 2 weekends here. But while its orbit is incredibly tight compared to Earth's, the ultra-cool red dwarf star is so dim that 1E receives only slightly less energy than our own planet. This means its stellar flux is comparable not to Antarctica or the Sahara, but to a mild, temperate region on Earth. The kind of climate where forests, grasslands, and oceans can all coexist. Size is the next striking similarity. TRAPPIST-1E is about 0.92 times Earth's radius, and roughly 0.77 Earth masses. It should be noted that this translates into surface gravity only modestly lower than what we feel right now, perhaps around 80 to 90% of Earth's pull. You would not float like an astronaut, but your steps might feel a little lighter, your jumps a little higher. Crucially, that gravity is more than strong enough to hang on to a substantial atmosphere if one is formed and survived the star's early tantrums. Density gives us another vital clue. When scientists combine its mass and radius, TRAPPIST-1E comes out with a density very close to Earth's. This means we are almost certainly dealing with a rocky planet with a significant iron core, not a puffy gas-dominated mini-Neptune. In other words, we are looking at a solid surface, a world of rock, metal, and potentially liquid water, rather than endless clouds over a deep, crushing envelope of hydrogen and helium. Now place that rocky sphere in its cosmic neighborhood. Among the 7 planets, TRAPPIST-1E sits almost exactly in the middle of the classical Goldilocks zone. Not too close, not too far. Optimistically speaking, that position makes it theoretically capable of sustaining liquid water on its surface, provided the atmosphere is thick enough to spread heat from its eternal day side and thin enough to avoid a Venus-like runaway greenhouse. So it's time to find out the truth. If we could somehow teleport to TRAPPIST 1e, what would actually greet us when the airlock door opened? Would we step out into breathable air under a dim but steady red sun with liquid oceans lapping against alien shores? Or would our first glimpse be of bare rock, vacuum, and ice, a silent world that only looks Earth-like from 40 light-years away? The data from JWST are starting to narrow those possibilities, and in the next section, we will see just how far that verdict has already gone. Locked in place. What a day on TRAPPIST 1 really means. To answer that, we have to tackle something deceptively simple. What does a day even mean on TRAPPIST 1? On Earth, day and night chase each other around the globe. But on TRAPPIST 1, that dance almost certainly ended a very long time ago. In a compact system like TRAPPIST 1, tidal forces are relentless. When a planet orbits very close to its star, gravity stretches it slightly, raising permanent bulges. Over millions to billions of years, those bulges act like brakes, bleeding off rotational energy until the planet's rotation period matches its orbital period. This state is called tidal locking. One hemisphere ends up permanently facing the star, the other turned forever away. So it's time to find out the truth. TRAPPIST 1 orbits its red dwarf in just 6.1 Earth days and sits deep in the star's gravity well. All the data we have and all our models of such systems point to the same conclusion. TRAPPIST 1e is almost certainly tidally locked, with a fixed day side and a fixed night side. This means the basic rhythm that structures our lives on Earth simply does not exist there. What does that do to the geography of light? Imagine a blazing hemisphere where the red dwarf hangs in the same spot in the sky, forever. Near the substellar point, the star would be high overhead, bathing the ground in a steady, ruddy glow. Walk outward, toward the edge of the day side, and the star sinks toward the horizon, frozen in a perpetual late afternoon. Cross the line where day meets night, and you enter the terminator, a ring-shaped zone of eternal sunrise on one side, eternal sunset on the other. Now for the pattern interrupt. Picture standing in that twilight belt. You wait for the star to rise higher, but it never does. You wait for darkness, but it never comes. Time is no longer written in moving shadows, but in subtle changes of wind, temperature, and perhaps the slow drift of clouds. In the hunt for alien life, this is not a minor detail. It is the canvas on which everything else is painted. On the night side, the sky would be breathtaking. With the star permanently below the horizon, you would see a dome of stars, unspoiled by any sunrise. The other TRAPPIST 1 planets, packed tightly into the Goldilocks zone and beyond, could shine as bright, colored moons, sliding slowly across the sky over days. On the day side, by contrast, the red dwarf would loom large and dim compared to our sun, a steady ember rather than a blazing disk. It should be noted that this locked geometry does more than sculpt the sky. It sets up extreme potential temperature contrasts, dictates how any atmosphere must move heat around, and carves out likely habitable regions along the terminator. Optimistically speaking, it even shapes how an intelligent civilization would tell time, navigate, and build ecosystems around a world where the heavens hardly move at all. So let's begin to explore what that means for climate, oceans, and the real chances that TRAPPIST 1e could host life. Eyeball Earths and twilight belts, possible climates on 1e. On a tidally locked world where the star never rises or sets, what does climate even mean? It should be noted that on TRAPPIST 1e, the answer might be far stranger and more beautiful than anything on Earth. Planetary scientists have a name for one of the most striking possibilities, the eyeball Earth. Imagine TRAPPIST 1e with a permanent dayside ocean, liquid, and dark, centered directly under the red dwarf. Around it, stretching away into the endless night, the surface freezes into bright ice. From space, the contrast between that dark central sea and the surrounding white shell would look like a giant eye staring back at the star. In the hunt for alien life, this is one of the most iconic mental images we have. But how do we get an eyeball Earth? And when does it turn into something more familiar? This means we have to talk about the atmosphere. If TRAPPIST-1e only had a thin veil of gas, heat from the substellar point would not travel very far. The result would be a small, extremely hot, liquid patch under the star, with temperatures potentially above tropical Earth, while almost everything else, dayside and nightside, locks into deep freeze. A world of extremes, with habitability squeezed into a tiny oasis. Now imagine we dial up the air to something closer to Earth-like pressure. A thicker atmosphere is much better at moving heat around the planet. Winds would race from the scorching dayside to the nightside, spreading warmth and smoothing out the worst temperature spikes. Instead of a tiny hotspot, we could get a broad twilight belt, a ring of moderate temperatures wrapped around the terminator, where the star forever hugs the horizon. Could forests, oceans, and maybe even cities line that eternal sunset zone? So it's time to find out the truth about an even thicker option. If TRAPPIST-1e carried a dense, CO2-rich atmosphere, it might resemble a milder version of Venus, but at the right distance in the Goldilocks zone. In that case, the entire planet could be warm, with much smaller contrasts between day and night. Cloud decks could reflect some of the red dwarf's light, while greenhouse gases trap infrared heat, creating a more uniform, possibly very humid global climate. Optimistically speaking, that could mean oceans that never quite freeze, even on the night side. Oceans themselves are climate engines. A global ocean on TRAPPIST-1e would act as a vast heat reservoir, absorbing energy under the star and transporting it through currents into the darkness. But if large continents exist, the story changes. Land breaks up currents and can cool rapidly, so we might see blistering desert near the substellar point, rugged coastlines along the twilight belt, and colossal ice caps buried on the night side, kilometers thick. So let's begin to connect this to real data. JWST's first thermal measurements are already ruling out some of the most extreme cases, trimming away the wildest eyeball and Venus-like scenarios. But which climate regimes survive? And where life, and any future alien skylines, would most likely cluster on TRAPPIST-1e depends on one more crucial piece of evidence we have only just started to measure. JWST's first clues. Is TRAPPIST-1e a bare rock or a breathing world? So it's time to find out the truth. When JWST stares at the TRAPPIST-1 system, is it seeing a family of bare rocks? Or is there at least one breathing world in the mix? Because in the hunt for alien life, this difference is absolutely everything. We should start with the planets we actually have solid measurements for. JWST has already watched TRAPPIST-1b and 1c slip behind their red dwarf star, measuring their thermal glow directly. What did it find? No signs of thick, puffy hydrogen blankets. Their infrared spectra look almost like hot, exposed rock, with dayside temperatures consistent with airless or nearly airless surfaces. This means those inner worlds are almost certainly not wrapped in Neptune-like envelopes. But while B and C are too close in to be habitable, they act as our laboratory for the whole system. If TRAPPIST-1e had a similarly thick hydrogen atmosphere, its extended, low-density envelope would leave a strong fingerprint in JWST's data. Hydrogen is excellent at puffing up a planet's radius and altering the way it emits heat. Models that match B and C tell us that at TRAPPIST-1e's orbit, such a primordial envelope should still be obvious. It should be noted that we do not see that kind of dramatic signature so far, which makes a massive hydrogen shroud for 1e less and less likely. So what about temperature? For a bare rock locked in a 6-day orbit, constantly facing its star, the day side should roast, while the night side freezes in darkness. JWST's early constraints and climate models bracket 1E's dayside brightness temperature between two extremes: a searing, almost lunar landscape if there is no atmosphere, and a cooler, more even glow if air, and possibly oceans, redistribute heat. If future measurements place 1E well below the bare rock prediction, that will be a strong hint that something, winds, clouds, maybe even weather, is carrying energy to the night. Here is the twist. The apparent lack of a puffy hydrogen atmosphere is actually good news for habitability. A Neptune-like envelope would crush any surface under immense pressure and trap heat until the planet became a mini gas giant. By ruling that out, JWST increases the odds that if TRAPPIST-1e has an atmosphere at all, it is more Earth-like or Venus-like, dominated by nitrogen, oxygen, or CO2, not hydrogen and helium. Optimistically speaking, that keeps liquid water and a solid surface firmly on the table. So let's begin to sum up. The current data tell us that TRAPPIST-1e is almost certainly rocky, almost certainly not a mini Neptune, and still very much a candidate for a temperate, Goldilocks zone world. But does it have a thick, swirling atmosphere? A thin, Mars-like veil? Or nothing at all? The jury is still out, and that uncertainty is exactly what makes imagining its surface so compelling. Because if we want to picture alien oceans, skies, and even civilizations, we first need to know, what would a day on TRAPPIST-1e actually feel like? Walking the Terminator, where would we actually live? So if TRAPPIST-1e is tidally locked, where would anything actually live? In the hunt for alien life, that is not a trivial question. One hemisphere bakes under eternal day, the other freezes under endless night. But between them, there is a narrow ring that might be just right. This is the Terminator Zone, the permanent twilight circle where the star forever hovers near the horizon. If TRAPPIST-1e has a reasonably thick atmosphere, and maybe even oceans to move heat around, this ring could be the true Goldilocks zone on an already Goldilocks zone planet. Temperatures here might hover near Earth-like values, cool but not icy toward the dark side, warm but not scorching toward the light. So let's begin to actually stand there in our minds. Imagine a settlement stretched along this ring, a continuous chain of cities and habitats encircling the planet. Look one way, and the horizon glows with a perpetual sunrise, the red dwarf star pinned low in the sky, its dim orange light scattered through thick clouds. Look the other way, and the landscape fades into deep blue twilight, and then star-filled black, with the rest of the TRAPPIST-1 system hanging like a jeweled arc. This means infrastructure would not be random. It would follow the light. On the brightward side, immense solar farms march a little closer to the day side, pushing into harsher territory to drink in more energy. Panels there might face a fixed star, never needing to track across the sky, optimized for that single, unchanging angle of light. On the darkward side, the cold becomes an asset. Radiative cooling fields could stretch into the night, dumping waste heat straight into space. Farther still, observatories would sit under a perfectly stable sky, no sunrise to interrupt long observations of the universe. It should be noted that for astronomers, TRAPPIST-1e's night side would be a dream. Permanent darkness, thin, high clouds, and neighboring planets regularly transiting the face of their star. In between, in the comfortable middle of the ring, is where most people would live. Habitation zones would hug the band, where liquid water is stable at the surface, where pipes do not freeze and crops do not boil. Cities might be elongated east-west, always oriented along the Terminator, with transport lines circling the planet rather than crisscrossing it. But what about the weather in such a strange arrangement? With one side heated constantly and the other constantly cooled, we would expect powerful day-to-night winds roaring from the hot substellar region toward the frigid night side. High above, the atmosphere could develop super-rotating jets, fast rivers of air whipping around the planet, redistributing heat and moisture. Storm systems might not drift east-west like on Earth, but instead form great bands that circle the twilight ring, marching endlessly around the world. Optimistically speaking, that kind of circulation could smooth out extremes and make the Terminator surprisingly stable and surprisingly habitable. Yet to understand daily life here, we have to zoom in even more. What does that red star really look like from the ground? How does the slightly lower gravity feel underfoot? And on a world without sunrise or sunset, what would a single day even mean to someone born on TRAPPIST-1? So it's time to find out the truth about life in a sky that never moves. Under a red sun, sky, seasons, and gravity on one N. So let's begin with the most obvious question. If you looked up from the surface of TRAPPIST-1N, what would you actually see? Above you, the star would hang in a fixed position, a deep ember in the sky. TRAPPIST-1 would look larger than our sun does from Earth, but not blinding white. Instead, it would glow a rich red-orange, like a smoldering coal or a sunset frozen at noon. This means the landscape would be washed in a coppery daylight, bright enough to see clearly, yet softer and dimmer in the colors our eyes are used to. But while our sun pours most of its energy into the visible band, this red dwarf leans heavily into the infrared. It should be noted that our eyes evolved under a different spectrum, so on 1th, our perception would be subtly wrong-footed. Green plants, if they evolved here, might favor darker pigments to harvest that red and infrared light. Forests might look almost black, or a deep maroon carpet under the star, rather than the bright emerald we associate with an Earth-like world. What about the sky itself? On Earth, molecules in the atmosphere scatter blue light more efficiently, so our sky turns bright blue. Under a redder star, less blue light is available to scatter in the first place. Depending on the exact composition and thickness of the atmosphere, the sky over TRAPPIST-1e could be a darker, muted blue, or even drift toward violet or wine-colored hues near the horizon. Imagine standing in permanent late afternoon light under a sky that never quite reaches midday blue. And how would your body feel on this planet? TRAPPIST-1e's gravity is probably around 90% of Earth's. Not Moon-like, not Mars-like, just subtly lighter. You would walk almost normally, but your steps would feel springier. You could lift loads you might struggle with on Earth, and your jumps would carry you a little higher and a little farther. In the hunt for alien life, this is an unusually gentle adjustment. Time, however, would feel far stranger. Because the planet is tidally locked, most locations never see a sunrise or sunset. The star simply hangs there, forever. On the night side, it never rises. On the day side, it never sets. With a nearly upright axis, there might be almost no seasons, only small shifts in climate driven by atmospheric dynamics. So how do you mark a day when the sky refuses to tick? Here's the pattern interrupt. Your clock would not follow the sky at all. Instead, societies on TRAPPIST-1e might define time by the 6.1-day orbit, by the subtle gravitational tugs of neighboring planets in the system, or purely by artificial clocks and social convention. Optimistically speaking, that unchanging red sun and weak seasonal rhythm would reshape everything. Biology tuned to permanent light or dark, psychology adapted to a sky that never moves, and culture built around mechanical time rather than celestial cycles. So it's time to find out the truth about how climate, oceans, and possible ecosystems could organize themselves on such a world, and whether TRAPPIST-1e can truly stay in the Goldilocks zone for life. Alien photosynthesis, how life could drink red starlight. If TRAPPIST-1e really sits in the Goldilocks zone for life, we have to ask a strange question. What does sunlight even mean on a world where the star glows deep red? On this planet, photosynthesis would be playing by very different rules. TRAPPIST-1 is an ultra-cool red dwarf, which means most of its energy does not come out as bright yellow-white like our sun. Instead, it pours power into deep red and infrared wavelengths, light that is almost more like gentle heat than the sharp glare we know. This means any photosynthetic organism on TRAPPIST-1e would need pigments tuned away from Earth's familiar green chlorophyll, reaching further into the red, maybe even far into the infrared. In the hunt for alien life, that shift in color could be the first big clue. So what would alien plants look like under that crimson sky? On Earth, leaves are green because chlorophyll reflects green light and absorbs red and blue. But while that works well under our star, it would waste precious energy here. On TRAPPIST-1e, it should be noted that evolution would be under intense pressure to capture every photon it can. Foliage might be so dark it appears almost black, absorbing nearly the entire visible and near-infrared spectrum. To do that, organisms might layer multiple pigment systems in the same leaf-like structure, each tuned to a slightly different wavelength band. One pigment could grab the deep red, another the near-infrared, another still reaching into even longer wavelengths. Together, they would form a biological solar panel designed for a dim red universe. Would forests of this world look like vast, matte black carpets stretching toward the substellar point, drinking in the glow of a star that never moves? Because TRAPPIST-1e is almost certainly tidally locked, the day side receives constant irradiation, while the night side never sees the star at all. There is no sunrise or sunset, no daily cycle to anchor a biological clock. This means growth patterns would be driven less by day and night, and more by slow changes in temperature, nutrients, or perhaps rare stellar flares. On the bright hemisphere, metabolism could be steady and unhurried, with organisms photosynthesizing continuously at a low rate. Around the terminator zone, in permanent twilight, life might specialize in dim light harvesting, balancing weaker energy with more moderate temperatures. What about the oceans? Optimistically speaking, if TRAPPIST-1e has deep global seas, water would shield life from the remaining high-energy radiation from the star. Near the surface, on the day side, photosynthetic microbes could form a thin, dark layer, tuned to soak up red and infrared light that penetrates only a short distance. Below that, where light fades to black, chemosynthetic ecosystems might cluster around hydrothermal vents, using chemical energy from the planet's interior, just as life does at Earth's mid-ocean ridges. If complex life evolved in such a system, its entire sensory world would be anchored to this alien light. Eyes, if they exist, might be most sensitive in the deep red and infrared, seeing heat contrasts more clearly than color. Navigation could be based on the fixed position of the star on the horizon or overhead, and on subtle gradients of warmth and brightness rather than moving shadows. Even the very idea of east and west might be meaningless. Instead, directions could be defined as toward the star, away from the star, and along the line of twilight. So let's begin to imagine what that would feel like, not just for plants, but for entire food webs and perhaps even civilizations. Because once we understand how energy flows through these alien ecosystems, we can start to ask a deeper question. How stable are they over billions of years under a red dwarf? And does TRAPPIST-1e truly have enough time and calm to let them flourish? Predators in perpetual twilight. Complex life on 1e. So if the plants are clinging to that endless twilight, what about the animals that eat them? In the hunt for alien life, we often picture microbes or simple algae, but on TRAPPIST-1e, the physics of the Terminator could just as easily support herds, hunters, and entire food webs. Imagine herbivore analogs moving slowly across the Goldilocks zone, always keeping the red dwarf fixed to one side of the sky. The light is low, coppery, and forever slanting, so eyes here would not look like ours. They might be huge, with oversized pupils and reflective layers like a cat's, or replaced entirely by pressure and heat sensors spread across their skin, mapping the dim landscape by gradients of temperature instead of color. On a world where the illumination never changes direction, their bodies could grow long, horizontal frills that always face the star, doubling as both solar warmers and sensory arrays. But where there are grazers, there are predators. How do you stalk prey on a planet with no nightfall to hide in? This is where the stark boundary between day and dark becomes a weapon. A hunter lurking just inside the deeper shadow of the night side could watch silhouettes drift through the twilight, striking from concealment as prey cross from brighter to darker ground. Others might patrol in great circles around the planet, forever following the most comfortable temperature band as it meanders with weather and seasons defined not by day-night, but by slow orbital changes. It should be noted that TRAPPIST-1E's gravity is slightly lower than Earth's, and if the atmosphere is thick and oxygen-rich, this means bodies can get big. We could see towering, column-like grazers using their extra height to access high, star-facing foliage with broad, load-bearing limbs adapted to the softer pole. Respiratory systems might be deeply layered, branching air sacs or countercurrent blood flows, tuned to squeeze every bit of usable gas from an atmosphere that may have very different pressures and compositions from our own. Optimistically speaking, even gliding or ballooning organisms could drift along the temperature gradient, surfing gentle winds that constantly flow from day to night. Without a sunrise or sunset, though, how do these creatures know when to rest? Instead of a daily sleep-wake rhythm, behavior might be organized into ultradian cycles, short bursts of activity and recovery, repeating many times during a 6.1-day orbit. Internal biochemical clocks, driven by tides, temperature pulses, or even magnetic variations from the star, could replace our reliance on light. Predators might synchronize group hunts to subtle atmospheric waves, while prey time their migrations to long, slow climate oscillations that we would not even notice at first. So it's time to find out the truth about what that would do to a mind. If intelligence emerged here, its sense of time, direction, and even the idea of a day would be utterly alien, and the way such a civilization measures its history could change how we search for their signals next. Civilizations under a frozen sky, building a society on 1E. If their minds are shaped by a world without days, what would their cities look like? On TRAPPIST-1E, intelligence would not just adapt to the planet, it would wrap itself around the thin ring where life can survive. Urban planning would start with the Terminator itself. Instead of circular cities with suburbs radiating outward, imagine elongated, ribbon-like megacities tracing the habitable ring. Streets and transit lines would run mostly east-west, forever parallel to the shifting boundary between bright and dark. Need to go inland? That does not mean north or south, but closer to the star or deeper toward the frozen night. This means their mental map of the planet is not a globe with poles, but a band, lightward and darkward, up orbit and down orbit. Transportation would follow this logic. High-speed rail or vacuum tube lines would loop circumferentially around the planet, linking arc after arc of the ring. You would board a train, not to cross continents, but to slide along a narrow, habitable belt that encircles the whole world. It should be noted that any attempt to build too far into the day side risks scorching heat, while too far into the night side brings lethal cold. Energy infrastructure would exploit those extremes. On the day side, great forests of solar towers would march sunward, drinking in the red dwarf's steady glow. Closer to the dark, vast thermal plants would tap the temperature gradient, running heat engines between the warm air of the Terminator and the deep cold of the night. Optimistically speaking, this gradient could power a civilization for geological timescales. Data centers would retreat into the night side, where natural cold makes cooling trivial, while observatories would stare out from the eternal dark, using the absence of scattered light to map the universe with exquisite precision. But how do you navigate a sky where the star never rises or sets? On TRAPPIST-1e, the star is nailed to one point in the sky, so direction is defined by it. Toward star and away from star replace east and west. Above the horizon, neighboring planets in the TRAPPIST-1 system would regularly parade past, moving with clockwork precision. Their resonant orbits form a celestial metronome. Calendars might be built not on days, but on conjunctions. Every time one E, one D, and one F line up, another unit of history passes. In the hunt for alien life, culture is as revealing as biology. Myths here would almost certainly focus on the boundary between light and dark. The blazing dayside could become a realm of trial or transcendence, the frozen night a place of memory or death. Philosophers might build entire traditions around gradients instead of cycles, not sunrise and sunset, but the continuous change of temperature, wind, and light as you walk lightward or darkward. Art would obsess over the unmoving star, playing with shadows that never rotate, only stretch and sharpen with weather. So let's begin to ask a harder question. If such a civilization exists on TRAPPIST-1e, what does their science say about us? Do they already have our pale sun charted as a distant, unremarkable star? Perhaps with one intriguing, slightly too bright, radio-loud planet? And across 40 light-years, with both of us bound to our own Goldilocks zones, could we ever manage more than a brief, flickering conversation? Looking up from 1E, how would they discover us? From their side, we are the mystery. If there is a thinking species on TRAPPIST-1e, what would their telescopes see when they look back across 40 light-years toward us? To them, our sun would be just another faint, yellow-white point in a crowded sky, far less dramatic than their nearby red dwarf. It would not flare and simmer in deep crimson like their own star. It would simply sit there, almost boring. But while it might look unremarkable to the eye, the moment they start doing precision astronomy, everything changes. With sensitive instruments, they could watch that tiny point of light dip ever so slightly as Earth passes in front of it. This means they could discover us the same way we discovered them, through transits and subtle stellar wobbles. Each time Earth crosses the sun, the light would dim by less than 1 part in 10,000. Hard to see, but not impossible for a civilization that has measured the intricate clockwork of 7 planets in their own system. They might even notice Jupiter tugging on the sun, using radial velocity to weigh our planets as the star shifts back and forth in space. It should be noted that TRAPPIST-1e gives its observers an advantage we do not have. Their sky hardly moves. The star above the dayside is fixed in place. The constellations over the night side never rise or set. No spinning planet to smear out long exposures. No sunrise to interrupt a crucial observation run. From the eternal night hemisphere, they could build observatories that stare at our sun for weeks or months at a time, uninterrupted, pushing the limits of what their data can reveal. But what would they think a habitable world looks like? In the hunt for alien life, we use our own sun and Earth as the template. They would not. Their Goldilocks zone hugs a cool, dim red dwarf. To them, a bright, energetic star like the sun might initially look dangerous or simply inefficient. Why waste so much light and heat? Optimistically speaking, they might even dismiss sun-like stars at first as poor candidates for calm, long-lived, Earth-like planets. Then comes the pattern interrupt in their thinking, Earth's signal. If they split our starlight during transits, they could see oxygen, ozone, and traces of methane in our atmosphere. That combination would be very hard to explain without life. They might infer a world with rapid day-night cycles, strong seasons, and restless weather, utterly unlike their tidally locked, slow-changing climate. So it's time to find out the truth about this symmetry. As we struggle to decode a single pixel of TRAPPIST-1e, they would be doing the same with us, each side wondering whether that distant, flickering planet is inhabited or just silently waiting. Could we ever go there? The engineering and time problem. So if there is someone on TRAPPIST-1e staring back at our sun right now, could we ever meet them? In the hunt for alien life, this is where the romance of discovery slams into the hard wall of engineering. TRAPPIST-1 is close by cosmic standards, but not by human ones. It sits about 40 light-years away. This means even light itself takes 4 decades to cross the gap. Our fastest spacecraft, so far, like the Voyager probes, would need tens of thousands of years to make that trip. We cannot design a mission that lasts longer than our entire recorded history and still pretend it is practical. So let's begin with the obvious question. Can we go faster? Concepts like nuclear fusion drives promise exhaust velocities far beyond chemical rockets. Beamed light sails, pushed by powerful lasers from the solar system, could, in principle, accelerate tiny probes to a significant fraction of light speed. Antimatter engines, at least on paper, offer even higher performance. But while these ideas sound like science fiction, even optimistic versions would still take decades to a century or more to reach a planet 40 light-years away. It should be noted that there is a huge difference between sending a gram-scale probe and sending a person. A robotic wafer sail, like a more advanced version of the breakthrough Starshot concept, does not need food, water, radiation shielding, or space to move around. It can tolerate brutal accelerations and harsh cosmic rays. A human crew cannot. Life support systems must recycle air and water for decades. Shielding must protect against the red dwarf's flares and the interstellar environment. And the psychological strain of a lifetime spent in a metal cylinder has to be survivable. Suddenly, what is merely difficult for a machine becomes almost impossible for a biological body. This is why many scientists talk about interstellar precursor missions. Before we even dream of crewed starships, we could send small, high-speed robotic scouts to nearby stars, including this compact system around a cool red dwarf. A flyby probe racing through the TRAPPIST-1 system could map each planet, sniff their atmospheres, and send back detailed data. A more advanced mission might even break into orbit around TRAPPIST-1e, turning it from a single pixel into a fully characterized Earth-like world. Optimistically speaking, that kind of robotic exploration might be a project for the next few centuries. But while we wait, JWST and whatever comes after it are our only windows into this distant Goldilocks zone. Every photon we collect from TRAPPIST-1e is precious, because for many generations, that faint, flickering light is all we will have. So if we cannot go there yet, what can we still learn from here? What TRAPPIST-1e teaches us about Earth. From here, TRAPPIST-1e does something subtle but profound. It turns into a mirror. When we model this distant, Earth-sized planet, we are really asking a question about ourselves. How fragile are the conditions that keep Earth habitable? If you swap our yellow sun for a cool red dwarf, stretch out the length of a day to match an orbit, and move the planet into a tighter Goldilocks zone, do you still get oceans and clouds, or something completely alien? In the hunt for alien life, that is not a side question. It is the question. This means TRAPPIST-1e is like a controlled experiment the universe has run for us. Same basic size, similar density, rocky composition, probably an iron core, but the context is wildly different. A tiny star, constant infrared light, and almost certain tidal locking. By tweaking just a few parameters, star type, rotation, orbital distance, we see how many different ways an Earth-like world could have turned out, and still, at least on paper, remained habitable. It should be noted that some of the most important lessons do not come come from pictures, but from climate models. When scientists simulate tidally locked planets like 1E, they are forced to think about how air and oceans move heat from a permanent day side to a permanent night side. Those same equations also describe how Earth's atmosphere responds to changing patterns of heating, stronger solar activity, or long-term shifts in circulation. In other words, every virtual storm on TRAPPIST-1 quietly improves our understanding of storms here at home. Atmospheric escape is another example. Around a red dwarf, high-energy radiation can strip away gases over billions of years. So how thick would 1E's atmosphere need to be to survive? How strong a magnetic field? These questions loop straight back to Earth. How did our own atmosphere endure the sun's more violent youth? What protects us from losing our air drop by drop into space? As JWST measures the mass and radius of these planets with increasing precision, something else becomes clear. Earth is not physically unique. TRAPPIST-1E and its siblings show that Earth-like size and density are repeatable outcomes of planet formation. Rocky worlds are not rare jewels. They are standard products of this galaxy-wide factory. So where is the real rarity? Optimistically speaking, it may lie in the delicate, long-term balance between atmosphere, magnetic field, and stellar behavior. Keep that trio aligned for a few billion years, and you might get forests, oceans, and technology. Let any one of them drift too far, and you could end up with a frozen husk or a runaway greenhouse. So it's time to find out the truth. Whether TRAPPIST-1E is lifeless or alive, it reframes Earth as one point in a vast design space of possible habitable worlds. And if this is just one example, what might the others look like up close? The future of the verdict, what JWST and beyond will reveal next. So what happens next when a maybe habitable world stops being just a theory and starts being a test? In the hunt for alien life, TRAPPIST-1E is about to move from interesting to interrogated. JWST has already taken its first hard look, but the real power of this telescope is time. Multiple programs are lined up to watch TRAPPIST-1E and its siblings over and over again. More transits, where the planet crosses the face of the star, secondary eclipses, where it slips behind the star, and even phase curves, tracking how the day side and night side glow as it orbits. Each of these gives us a different slice of information about temperature, atmosphere, and energy flow. Why repeat the same observations so many times? Because the signals we care about are tiny. A single transit spectrum might be dominated by noise from the red dwarf, the instrument, or even random cosmic rays. But stack 10, 20, or 30 of them together, and the random noise averages out, while real features add up. This means subtle fingerprints, like the deep, broad absorption bands of CO2, or the softer imprints of clouds and hazes, can finally rise above the background. It should be noted that this is already happening. For TRAPPIST-1B and 1C, stacked JWST data have ruled out thick atmospheres. For TRAPPIST-1E, future stacks could tell us whether there is a compact Earth-like mix of nitrogen and oxygen, a thinner Mars-like envelope, or something stranger, like a high-altitude haze that mutes everything beneath. Phase curves could reveal whether heat is efficiently moved from the day side to the night side, hinting at winds, oceans, or a bare, airless rock. Pattern interrupt. What if we did not just infer this world from shadows, but actually saw it? That is where the next generation comes in. On the ground, extremely large telescopes with mirrors 30 to 40 meters across will try to separate the faint light of planets from the glare of their stars. In space, concepts like LUVOIR or HABEX imagine giant, ultra-stable observatories using star shades or coronagraphs to directly image Earth-like planets around nearby stars, including cool red dwarfs. With that kind of hardware, we move from, is there an atmosphere, to, what exactly is in it? Could we pick out oxygen paired with methane, or other chemical combinations that are hard to sustain without biology? Optimistically speaking, TRAPPIST-1e is one of the best test cases we have for learning how to recognize biosignatures across the universe, even if our current data are nowhere near a definitive claim. So let's begin to see our moment clearly. JWST has already turned TRAPPIST-1e from a line in a catalog into a world with an emerging personality. Not Venus, not Mars, something intriguingly in between. Over the coming decades, new telescopes will either confirm it as a living planet with an active, complex atmosphere, or as a cautionary tale about how close a world can come to being habitable and still fall short. Either way, this one small planet will reshape how we imagine all the others. So, what would life be like on TRAPPIST-1e? So if TRAPPIST-1e really is that in-between world, what would it actually feel like to live there? In the hunt for alien life, this is where the equations and spectra finally turn into streets, skies, and seasons. First, we have to picture the stage. TRAPPIST-1e is almost Earth-sized, with gravity just a bit lower than ours. You would feel slightly lighter, but you would not be bouncing in slow motion. Above you, the red dwarf star is fixed in the sky, a deep orange disk that never rises and never sets. Because the planet is tidally locked, one hemisphere faces the star in eternal day, the other hides in endless night, and between them lies a narrow, habitable twilight ring where temperatures stay moderate if, and only if, a real atmosphere can move heat around. So, let's begin our day in that ring. Imagine waking in a city stretched along the Terminator, a chain of habitats following the line of perpetual sunrise. Outside your window, the star hangs low on the horizon, frozen in a permanent dawn. Shadows are long, colors are muted, and the sky glows copper and violet as starlight filters through a dense, Earth-like atmosphere. Clocks here do not track sunrise and sunset. Instead, people measure time by the 6.1-day orbit, by the resonance beats with neighboring planets, or by the subtle pulsations of the star itself. You step out into streets that always face the same direction. Starward and nightward are as important as north and south. This means navigation is almost effortless. The star is your compass, and at certain times, bright sibling planets B, C, D, and F gleam like lanterns, lined up along the same thin strip of sky. It should be noted that on a world with no conventional day-night cycle, culture would adapt. Work shifts might follow planetary conjunctions, or the regular transits that cast faint, predictable dimmings over the city. Beyond the buildings, dark-leaved forests hug the twilight zone. Photosynthetic organisms here have evolved to drink in red and infrared light, so vegetation might appear almost black, with a faint metallic sheen. On the dayside slopes, plants and plankton endure brighter, hotter conditions, adapted to constant illumination rather than daily cycles. On the night side, slow, cold ecosystems cling to residual heat, feeding on chemical energy and the atmospheric rivers that transport moisture from the starlit hemisphere. Optimistically speaking, an advanced civilization would exploit the planet's enormous thermal contrast. Vast energy farms straddle the boundary, using the temperature difference between day and night to drive turbines. High-altitude balloons ride steady winds that endlessly flow from hot to cold. Specialized expeditions push deeper into the dayside to study reflective cloud decks and into the nightside to mine exotic ices, always tethered to the safe band of habitability. So it's time to find out the truth. Is this just poetic speculation or a glimpse of something real? Every detail we have imagined is chained to actual physics, to JWST's data, and to what we know about tidally locked climates. And red dwarf systems like TRAPPIST-1 may be the rule, not the exception, in our galaxy. If life is common, many of its homes could look more like this world of eternal sunrise than our familiar Earth. But if such a civilization really existed on TRAPPIST-1e, what would they see when they finally turned their telescopes toward us? And how would we look from their endless dawn? From curiosity to responsibility, why TRAPPIST-1e matters to us. From their endless dawn, we would look like what to them? A stable blue world? Or a fragile experiment on the edge of failure? That question loops back on us. Because in the hunt for alien life around TRAPPIST-1e, we have really been holding up a mirror. So let's begin this part by looking at the path we have taken. We started with that huge existential question. Are we alone in the universe? Or is life written into the physics of planets and stars? From there, we narrowed down to a single, ultra-cool red dwarf, TRAPPIST-1, and its tightly packed system of 7 worlds. We explored how each planet orbits in that compressed clockwork, how their atmospheres, or lack of them, shape their fate, and why 1e, in the middle of the Goldilocks zone, stands out as the most Earth-like and potentially habitable. But while we have flown, in imagination, to that world of eternal sunrise, something else has been happening. Looking outward has sharpened how we see home. When JWST data show us how easily a thin atmosphere can be stripped from a planet close to its star, what does that say about our own? When we realize that a long-lived, quiet red dwarf with a stable habitable zone might be rare, we are reminded that our own Sun-Earth partnership is not guaranteed everywhere. This means TRAPPIST-1e is not just a distant curiosity, it is a case study in planetary fragility. The difference between a living ocean world and an airless rock may come down to details: magnetic fields, early flares, volcanic recycling of gases. It should be noted that those same balancing acts are at work on Earth right now. Our climate, our atmosphere, our biosphere all sit on similarly narrow ledges. So why are we so drawn to this one planet? Part of it is pure curiosity. We want to know whether chemistry plus time almost inevitably gives rise to life, or whether Earth is a spectacular exception. Could photosynthetic organisms adapt to the reddish light of a red dwarf star? Could a civilization learn to thrive under a sky that never changes? These questions are about them, but also about us. At the same time, there is a quieter, long-term motive. Optimistically speaking, if humanity endures for millennia, we might one day spread beyond the solar system, or at least learn from other systems how worlds survive or fail. Even if we never set foot on TRAPPIST-1e, understanding its climate, its orbit, and its possible atmospheres deepens our sense of what kinds of futures are physically allowed in this universe. So it's time to find out the truth about what happens next. TRAPPIST-1e is not a finished story. It is an unfolding one. As new data arrive, our picture of this planet will sharpen or be overturned. The real question is, how do we stay part of that story? And what will we do with what we learn? Your turn to visit TRAPPIST-1e from here. So where do we go from here? We have traced TRAPPIST-1e from raw numbers and light curves to possible oceans and civilizations under a fixed red sun. But now it is your turn to land there. If you could step out onto that temperate twilight ring, what would you build first? A compact shielded base at the substellar point? Or a chain of cities stretching around the Goldilocks zone between day and night? Imagine your first hour on the surface. The red dwarf star hangs in exactly the same place in the sky, never rising, never setting. Shadows never move. Winds may roar from the day side to the night side, carrying heat across the planet. Do you explore the bright hemisphere with its blazing red glare, or the dark side where only starlight and auroras paint the ice? What would you want to measure, sample, or listen for in the hunt for alien life? This means the story of TRAPPIST-1e is no longer just about astronomers and telescopes. It is also about how we imagine a truly different, yet still Earth-like, way to be habitable. So tell us in the comments, How would you live under a star that never moves? Would your cities hug the Terminator, powered by endless day, or dive underground, insulated from space and flare storms? It should be noted that every piece of this system's story has carried a surprise. For you, which part hit hardest? JWST's verdict that some planets are almost certainly airless rocks? The relentless tidal locking that freezes one hemisphere and scorches the other? The possibility of ocean worlds, or of ecosystems adapted to permanent evening under a dim red sky? Or was it the idea that a technological civilization could rise there, building its science and myths around a sky that barely changes at all? If you want to keep exploring, there is a whole gallery of worlds waiting. We can visit other promising exoplanets like Proxima b or the TOI 700 system, dive deeper into how red dwarf stars shape their planets, or follow JWST's latest data on atmospheres and biosignatures. Optimistically speaking, the next big clue about life beyond Earth may already be sitting in a telescope archive, waiting for us to understand it. So it's time to find out the truth together, over years, not minutes. If you would like to stay with us as new observations refine the verdict on TRAPPIST-1e and other alien Earth candidates, consider subscribing, liking, or sharing this video. That way, when the next spectrum drops, you are here when the story shifts. We began with a question: are we living on the only kind of habitable world? TRAPPIST-1e suggests the answer might be no. Somewhere, under a red star that never moves, another version of home could already exist. The next step is simple, but profound. We keep looking.